Hello everyone, welcome to my channel. In this series of video, I will try to demonstrate the most common questions that are very likely to be asked or examined in an A-level math exam. And in this particular video, I would like to show you a question, a very standard differential equation, but with some interesting extensions, which falls under the subcategory of integrations. Now, let's begin and have a look. A function f has domain reals and a range y in the reals and y is greater than or equal to e. In the graph, y is fx is shown, and the gradient of the curve at a point xy is given by dy over dx is x minus 1 bracket times exponential of x. Find an expression for fx. Fully justify your answer, 8 marker. Alright, you can see, for any question that is an 8 marker, you expect that it has some difficulties, at least it has some tricky points which you must have noticed. And the starting point for this question, I think it will be fairly obvious because we can see dy dx is some function, and obviously our goal is to find y. We're given dy dx, and initially the first thing we're going to do is just basically use an idea of differential equations. Okay, integrating dy dx and integrating x minus 1 ex. Obviously that doesn't make sense because we should have some differential operator here. And the common trick is we're going to take this dx to here, okay? So in a sense, please remember that differentiations, especially dy over dx, works in the same way as fractions. So if we have du over dv times dv over dt, it's equivalent to du over dt. That's exactly like how fractions work. And so back to our question, we may move dx to the right hand side to complete the both integrals. And you may question about this particular expression, like what is integral of dy? You may just regard it as, well, it's actually integrating 1 as a function, dy. And then integrating x times exponential of x minus exponential of x dx. We know that, well, integration of 1 is basically y, and for this particular expression, we know that minus ex is differentiated from minus ex, but for integral of xex dx, that's slightly trickier. We shall use integration by parts, right? Because you can see xex dx, we have a product of two separate functions. The main reason here also use differentiate by parts because I want to reduce it to something in the form of just ex or the linear multiple of ex. How? Well, the simplest thing we're going to do is take u to be x and du dx to be 1. Let dv dx to be ex. And obviously, then v is ex. If you're familiar with the solution, you can just write it down. So uv minus xex minus du dx times v an integral, so minus ex dx. And that would be xex minus 1, sorry, minus ex. To combine our equations, we have minus ex plus xex minus ex. Don't forget a constant, okay? Don't forget a constant, I nearly did. So y is xex minus 2ex plus some constant k. And we can check it by just differentiating the expression. dy dx is xex minus 2ex. But here we're going to differentiate by using our product rule. We're going to have xex and plus ex. So dy over dx is x minus 1 times ex. Exactly as they asked for. So we now know that our function y, objective function y, must be something of this form. However, you can see this question, they definitely ask you for an explicit expression for fx. You can't just keep the constant here. So we know that for first order ODE, okay, first order ODE, to have an explicit expression, explicit and unique solution, we must have some sort of initial conditions or boundary conditions, usually called initial conditions in this case. They will say, for example, at the point AB, YA is B. This is an initial value, which in the later differential equation course, if you further progress further on to math, you'll see that initial values are critical in terms of deciding whether a solution is unique or not, or even if the solution exists or not. Okay, so for this particular case, they did not provide us with such an very easy to observe initial value, but it still gives us a hint, right? Just think about it. How do they give us a hint? I mean, it should be some explicit values of the function y, right? Let's observe the graph of fx. Some might say, well, if we're able to know what's the value at the when x is 0, so basically the y-intersection, that might help. I mean, when you determine the equation of a straight line, we can always tell the y-intersection by its constant, isn't it? So they will believe something must work similarly here. However, dy dx would not usually tell you anything explicit about any intersections with y or x axes, but rather there are some other things we can think about, which are the turning points. You can see from the graph here that it must have a turning point at this point, right? And we know that it's at a minimum. If we are able to calculate the coordinate of this minimum turning point, then we have an initial value, and then hence we can solve the equation for an explicit and unique solution. Let's just observe the dy over dx. So we may say that, well, dy over dx is x minus 1 times ex, suggesting there is a turning point at x is 1, and from the graph we can tell y equals fx does indeed have a minimum at some point. At some positive value of x. Some positive value of x. We may further check what is the second derivative. Well, by using product rule, we know that must be x minus 1 ex plus 1 times ex, which is x ex, and at a point, and second order derivative at x is 1 is e greater than 0, suggesting that this turning point is indeed the minimum of y equals fx. So now we know that, well, there exists a point with a value 1 and the minimum value is on a curve. We had an x coordinate now. How do we know the y coordinate from the graph or from other informations? do you notice I always miss something here? It says y is reals and y is greater than or equal to e. You can see this function, the value is bounded from below by e, right? And it's a unique turning point, unique minimum. So we can assume that y is e as y greater than or equal to e. We know that this must be achieved by our minimum and only our minimum. So that implies our coordinate is 1e, okay? So this is the initial condition that we're starting with. So now we may complete the full solution. So we have said that y is x minus 2. So x minus 2 times ex plus some constant k. And we've shown that e is equivalent to 1 minus 2 just e, not ex, plus k. So e is minus e plus k. That implies k is 2e. Good stuff. So now y is x minus 2 times ex plus 2e. And that's the complete solution of this question with, I think, reasonable amount of argument, rigorous proof, actually. So let's just look back and summarize this question. The starting point is easy, okay? We find a general equation for this type of differential equations starting from here, which is not too difficult. I mean, ex, which is the easiest function that you can ever integrate or differentiate. And for ex, well, I think you must have, I'm sure you have encountered it so many times. So that you can, well, at the moment you see it, you know you're going to integrate it by integration by parts. And it should cause no difficulties for you to derive this part, right? But what really interesting is what proceeds on from here, okay? Because many people would know that, well, if we have initial value, then we can just substitute and solve for the constants. However, in this particular question, the initial value was not stated explicitly, okay? And that stops a lot of people from actually completing this question. But if we observe carefully, with all the information given us, there must be some special things about the graph connecting with its derivative, okay? We know that derivatives are most often used to calculate turning points, like a maxima, minima, whatever. In this case, it clearly demonstrates a unique minimum for this function y is fx, okay? And using differential equations, using your first order derivative, we can easily calculate the x-coordinate of the minimum. And then use some other informations, so the domain, the range. You can tell you that, well, that minimum must be achieved by your x is 1 because it is minimum. Okay, the function is bounded below. Function achieves minimum at e, and minimum x is 1 is unique. There's no any other turning points, hence no other minimum for this function. And you can see why, and that means y is e must be the y-coordinate of x is 1. Okay, that provides you a nice initial value. We can just substitute and proceed on. Okay. A bit more about first order ODEs. Initial values are extremely important. Okay. Actually more important than you think, because for some other, well, nicer functions, because the complexity of their function, of their graph, a not suitable starting points will not guarantee you the existence of roots, or will not guarantee you the uniqueness of a root, which is extremely not desirable. But hopefully, and in most cases, and I think in all cases, I think A-level questions will not ask you to discover and, well, examine any of these properties, it should be beyond the scope. But I think it's generally interesting because you may see, when we proceed on, there is a theorem called the Picard theorem, holds for differential equations, and giving some conditions on the functions, so for the differential equations, and the starting points, it tells you under what circumstances your differential equation and your initial values will give you a unique solution in your range. Okay. And sometimes you can see that the domain and the range also matters, because sometimes the function is repeated or not continuous on points, and then your solutions must be restricted to your continuous range. Okay, you can't achieve functions that's outside of continuous range. So, for example, y is 1 over x, right? It's discontinuous at a point, at x is 0. So if you achieve some solution in positive x, then you cannot assume it also holds for negative x, because given another starting point or another initial value where x is negative, you might achieve something very completely different. Okay. And I think that's all I want to say about this question, with some interesting extensions, if you're interested at all, for differential equations. And we can call it a day here. Okay, alright. I hope you have learned something useful from this question, and see you in the next video.